Okay, so we've introduced waves. We've talked about how to model them mathematically through the sine function. And now we're going to look at what happens when two waves overlap. And so that brings up the idea of interference and superposition. So let's start by looking at this figure from the textbook. This figure shows two pulses. Pulse on the left is traveling to the right, and the pulse on the right is traveling to the left. So these are two pulses with equal amplitude, and as we go down the figure, time is elapsing. And so in the second figure, the two pulses are closing in on each other, and then in this third portion, you can see that the pulses completely overlap, and what you get is what's known as a superposition of the structure of each pulse individually. And so at this third picture, we end up getting a pulse that has an amplitude of twice the individual amplitudes of the individual pulses. And then as time goes on, the pulses pass each other, and then at the end, you're left with two pulses, again, one traveling to the right, one traveling to the left, with amplitude A. All right, so when waves interact, when we say there's interference and that there's this superposition principle, we're simply saying that when more than one wave passes through a medium at the same position at the same time, that the resulting wave is just a combination of the individual waves that are passing through that point. Right, and so I've got another figure down here to highlight that point. The figure on the left demonstrates what we call, well, we don't want that. The figure on the left demonstrates what we refer to as constructive interference. So I've got a wave on the top and a identical wave in the middle. And when those two waves overlap, you'll notice that the peaks or the crests and the troughs exactly overlap. And so what's going to happen when we combine the two waves is that we're going to get a resulting wave down here that has twice the amplitude of either of the waves individually. All right, so that's constructive interference. That's when the crests and the troughs perfectly align. And then, of course, over here on this side, we have an example of what's known as destructive interference. And so again, on the top, I've got my wave, and then in the middle panel, I have a second wave. And you'll notice that the two waves have slightly different mathematical representations. The top wave has this plus pi term for the phase angle. And if you notice, what that does is it simply shifts. Here I have a trough for the top wave, and I've got a crest or a peak for the middle wave. Here I've got a crest for the top wave, but I've got a trough for the middle wave. And so this pi value here has essentially just shifted the top wave by half of a wavelength. And so when we go to add up the waves, the middle and the top wave together, what we end up with is 0 everywhere, right? Every time the top wave is at maximum amplitude in the upward direction, the middle wave is at maximum amplitude in the downward direction, and they exactly cancel out. Now you'll notice that also when the top wave crosses the equilibrium position, so does the middle wave. And so 0 plus 0 gives you 0, and so that's why we end up with this constant value of 0 for the right-hand side. So again, when the crests and troughs align, that's constructive interference. And on the other side, when the crests and troughs align, you end up with destructive interference. Now, having said all of that, in general, if we've got two waves that differ only by a phase shift, so pretty much exactly what we had in those last two figures, then the resulting wave, right, so the resulting wave, when you add the two waves together, the resulting wave is given by this expression. And so that's just combining this and this. Essentially, what we're doing is we're adding these two waves together. And it turns out, using some trig identities, you can turn this sum into this expression right here. Right? And the thing that you want to notice is that the amplitude of the resulting wave, right, is just given by this leading coefficient out front. And that means that the amplitude of the resulting wave is 2 times the amplitude of the original waves, right, because they had the same amplitude because they were identical other than the phase shift. And then you multiply that by the cosine of the phase angle divided by 2. All right. So now we're going to move on to looking at some specific phenomena related to superposition. All right, now that we've got waves moving and we know that when waves overlap, we can effectively add their values together, we can look at a particular application or result of this phenomena, and that's something known as standing waves. So standing waves result when traveling waves combine in such a way that they appear stationary. All right, and so I've got this figure here on the left. Zoom out just a little bit more. So I've got this figure, and we're going to focus in on a few of the panels in the figure to try to get a sense for what we mean by these standing waves. So the first thing that I want to do is focus on this top panel. So this is, it's actually two waves that are traveling, a red wave which is traveling to the left, and a blue wave which is traveling to the right. And in the top panel, you only see the red wave, and that's because the two waves are on top of each other. And so both waves are right there. Now, superposition principle says, well, if those waves are identical, then what you're going to get is you're going to get this resulting wave. All right, so that's the first snapshot. The second snapshot, sometime later, we look down at that next panel. You can see the red wave has moved a little bit, and the blue wave has moved a little bit. And no longer are those two waves exactly overlapping. And what that means is when you go to add the two together, right, the superposition principle, you end up getting a wave with a smaller overall amplitude. And in fact, if you look at the next panel, the waves have moved a little more, and now we're exactly at the right time where the crests of the red wave exactly align with the troughs of the blue wave, and that gives us a resulting wave of 0. And of course, I can keep going on with this, keep tracking this, but rather than doing that, I'm going to point out something interesting about that emerges even just with these first three pictures. So the interesting thing that I want to point out is that as these two waves are traveling and interacting, there are locations, there are positions where the resulting wave is always 0. And I'm just going to point out what those locations are in pink. Notice how everywhere that I'm drawing this pink vertical line, every wave that this line intersects is crossing the equilibrium position. So the wave is 0 at all of those locations, right? Regardless of which panel you look at. And those those positions are referred to as nodes, right? where the resulting wave is always 0. Now, there are also antinodes, and the antinodes are locations where the resulting wave is essentially maximum amplitude for that particular combination of waves, and that maximum amplitude oscillates between plus and minus the amplitude of the y value oscillates between plus and minus a from the original waves. And so where are those antinodes? Well, the antinodes are at these locations. And again, if I zoom back in here just real quick, we can follow along to see, let's focus on this spot right here. So this is an antinode. It'll correspond to the maximum displacement of the wave for that given superposition. And you can see as time goes on, even though this second panel is the maximum displacement, it's actually not as far off of the equilibrium as the top. And then the next, it actually intersects with the equilibrium position and now starts to go below the y-axis, the x equals, or the y equals 0 axis, and then bottoms out at minus a, then begins to travel back to the equilibrium, and then goes back towards a maximum amplitude of plus a. Right, so those are the antinodes. So we've got nodes and antinodes, and this is what's going to give rise to the standing wave phenomena. If you look at the bottom figure here, this is essentially all of those waves sort of plotted on top of each other. And what you can see is that we've got this really nice structure here where we've got nodes, and then we have these antinodes. Now, mathematically, we can identify the locations where the nodes and the antinodes are going to be just by using the property of the sine function. So nodes are going to be at locations where the sine of our argument, so sine kx, has to equal 0, right? The output of the function is 0 for the nodes, and so that puts a constraint on what the values of x can be. And so the values for x for nodes are constrained to be integer multiples of half of the wavelength of the wave that's that we're investigating. For antinodes, the wave doesn't have to be 0. It needs to be essentially the maximum value the wave can be, so that could be plus or minus 1. And so that puts a different constraint on what our values for x can be. So the positions of the antinodes then are integer multiples, odd integer multiples of the wavelength divided by 4, or quarter wavelengths. Right, so those are the two constraints that you have to get a standing wave. So the nodes, you'll get nodes at the locations where you have integer multiples of half wavelengths, and you'll get antinodes at integer multiples of the odd numbered quarter wavelengths. Okay, now we know about standing waves, and so we're going to look at this example where we've got a hanging mass connected to an oscillating mechanism by way of a string. All right, so the fact that we've got a hanging mass connected to this string means that we've got some tension in the string, and that means that we can determine what the speed of any wave that gets generated in this string is going to be related to the square root of the tension in the string divided by the linear mass density of the string. Now, if we want to investigate what types of standing waves are going to be possible to observe in this setup, we need to first realize that the string is connected or is stationary at the endpoints, and so those are going to be nodes. And so we essentially start off with our first possible wave being a wave where the only nodes are at the endpoints. And so what's the wavelength of that wave? Well, down here we've got it listed. A wave that goes through half of the oscillation in the full length of the string, and then undergoes the other part of the oscillation on the way back, that would be our first standing wave, the n equals 1 standing wave from the previous page. And so, remember, integer multiples of half wavelengths, and so 1/2 of this wavelength has to equal the length of the rope, and so you can determine that this first wavelength, the length of the first standing wave, has to be twice the length of the rope or the string. Now, the next standing wave will have nodes not only at the endpoints, but then also in the center. Right, so this would be the n equals 2 standing wave. And you can see that the wave will undergo one full oscillation in a distance L, and then will complete another full oscillation on the way back. So here, the wavelength has to be equal to the length of the rope. And so, again, we can rewrite that as this lambda 2 wavelength is 2 over 2L. And again, now if we want to go to the n equals 3 standing wave, now we need 2 nodes interior. And so when we do that, we get 1.5 wavelengths fit in the full length L, and then you get another 1.5 on the way back. So in this case, 3/2 lambda 3, right? 1.5 wavelengths fit in the length L of the rope. So that means the wavelength has to be 2/3 the length of the rope. And finally, the n equals 4 mode, 2 full wavelengths in the length of the rope, 2 full wavelengths on the way back. So here this means that lambda 4 is 1/2 the wavelength, right? You get 2 waves in a length L, so the wavelength is 1/2. All of this to say you can write out an expression for the wavelengths of the standing waves that are allowed in this system, and these wavelengths are 2 over n multiplied by the length of the string, where n can be any positive integer. Right, so these are known as the normal modes, these standing waves. And of course, if we have the wavelength, then we can immediately write out an expression for the frequency, because the wavelength times the frequency is the speed of the wave. And so down here, I've written out the expression for the frequencies that are allowed, and these are called the normal frequencies. And what I've done is I've swapped out for lambda, I've swapped out the speed divided by the frequency and then rearranged the terms. All right, and we are going to finish with an example problem. And so what I would recommend you do is that you pause the video right now and you work on this problem yourself. And once you finish the problem, then unpause and you can follow along with the solution. So this is the same setup that we were just looking at. We've got a string attached to a hanging mass over a frictionless massless pulley, and we're given the hanging mass value of 2 kilograms. We're given the linear mass density of the string, and we're given the length of the string. All right, so pause the video here and work out the problem on your own, and then come back and we'll work it out together. All right, welcome back. So the first question, part A here, is to find the speed that the waves are traveling along the string. And so the speed is related to the tension in the string divided by the linear mass density. Right, so this string right here is wrapped over this pulley and connected to this hanging mass, and since the pulley is frictionless and massless, the tension in the string is the same everywhere. And so that means if we can figure out the tension over here, then we essentially know the tension here. All right, so how are we going to find the tension in that first location? Well, we're going to do force analysis because we've got this hanging mass that's in equilibrium. Right, so how do we do force analysis? We start with a free body diagram. We identify the forces. In this case, it's rather straightforward. I've got the weight down, and I've got the tension force. Use the notation of the book. I've got the tension force up. And of course, what we do next is Newton's second law. So F net in the y direction is going to equal that friction force, or that tension force, minus the weight force. And since this is in equilibrium, that's got to add up to 0. And so the tension force has to be equal in magnitude to the weight of the hanging mass. So that allows us to immediately go back to our expression over here, and we can write out that the speed that the wave is going to travel is going to be 2 kilograms multiplied by 9.8 meter per second squared divided by the 0.006 kilogram per meter. And that works out to be 57.2 meters per second. And so there's the speed of our waves that are going to travel on this rope. Right, entirely determined by the tension, so by what that hanging mass was and the linear mass density of the string itself. Now, part B asks us to sketch out the first 3 normal modes. So for part B, sketch out the first 3 normal modes. Well, the 3 normal modes are going to be, the first mode is going to be when half of the full wavelength fits along the entire length of the rope. And so that's going to look like this. So there's the first mode. This is the n equals 1. Now, what's the wavelength for that? Well, the wavelength, remember, 1/2 lambda 1 has to equal L. And so that means that lambda 1 is equal to 4 meters for this first one. Now, the second mode is going to have nodes at the end and then 1 in the middle. And now I need something like that. So this is n equals 2. And so again, 2 over 2 lambda 1 equals L. And so that's going to give us, I guess I don't need the 2 over 2 there. So lambda 2 equals L, so our lambda 2 is equal to 2 meters. And then our n equals 3 is going to have our 2 nodes at the ends, and then nodes spaced, evenly spaced throughout the middle. And now if I sketch that, I do a terrible job, but you get the idea. So this is n equals 3. This is 3 halves. Lambda 3 equals L, right? 1.5 wavelengths fit in that full length, and so lambda 3 is going to equal 2/3 of the length, so that's 1.33 meters. So there's our part B. Those are the first 3 normal modes and the wavelengths that correspond to those. And I'm almost out of space, but I think we can fit it in. For part C, I want the frequencies that correspond to these first 3 normal modes. And so we've got F1 equals the speed of the wave divided by lambda 1. So that's going to be our 57.2 meters per second divided by our 4 meters. So that's about 14.3 hertz, or inverse seconds. The second frequency is going to be the speed divided by lambda 2. So 57.2 meters per second divided by 2 meters. And that's going to be about 28.6 hertz. And then F3, the third frequency here, you get the idea. 57.2 meters per second divided by 1.33 meters. And we get about 42.9 hertz. So those are the first 3 normal frequencies for these normal modes for this particular setup. And that's the end of this problem.